Hess was one of the early thermochemists. He was Swiss-born and he lived in Russia most of his life. He did a lot of work on the conservation of energy, and in particular today we're going to apply that to enthalpy changes in reactions. If we take an enthalpy profile diagram, such as this one here, we have an enthalpy change between the reactants and the products. And we know from experiments that that has a certain change in enthalpy. So I'm going to label that delta H in red. Now, there's other ways that we could get from the reactants to the products. For example, purely theoretically, we could break them up into single atoms, and we could break all of the bonds in the molecule. That would take an awful lot of energy. So in that case, we would have to go up to a much higher energy state. And then when the bonds reformed, we'd end up releasing a lot of energy to come back down to the original level. And I'm going to label this the change in enthalpy to make the reactants into atoms. I'm going to label that in green with a delta H, and then I'm going to label in blue, while coming back down, another enthalpy change. So you can see by the fact that this is a graph, if we start off here, we always end up here. It doesn't matter whether we go straight there, through the red route, or if we go to green, and then through the blue arrow as well. However we do it, we will always end up at the same level after the reaction as before the reaction. And we could have a catalyst, and we could have different intermediates. We could have them up here, and then we could go through other intermediates, and we'd eventually get to the products. We'd still overall have the same enthalpy change. And that's really Hess's big idea. It was that whatever route you take between a reactant and a product, then the total enthalpy change, which I've got in red there, is equal to the sum of the other enthalpy changes through the other routes. Let's take a generic example. So I've called this chemical A and chemical B. Let's say that chemical A turns into chemical B with this enthalpy change. We could also make chemical B by turning chemical A first into, let's say, chemical C, which then turns into chemical B. And again, I'm going to label these with their enthalpy changes as well. So we can mathematically say that this change in enthalpy, the red one, between A and B, is equal to the sum of these two, because we're adding them together. We're going this way and then we're going this way. And that's quite useful because sometimes we'll know enthalpy change in red there at the top between A and B, and we'll know the enthalpy change between A and C. But we want to work out, or it's impossible to measure for various reasons, or practical reasons, for example. It's impossible to measure this one. But we might need that data. We might need that data to work out whether another reaction is feasible. So how do we do it? Well, we can rearrange this to make this enthalpy change here the subject, because if A to B equals A to C to B, so the red one equals the sum of the blue and the green ones, and just a little bit of algebra, the blue one on its own will equal the red one minus the green one. Here's an example of a reaction which would be difficult to measure. We've got carbon and hydrogen forming cyclohexane here. And if you take some carbon and you take some hydrogen and you crank up the pressure and you put a load of energy in, you'll probably get any number of different isomers. It's almost impossible to actually make pure cyclohexane out of these, and therefore the enthalpy change of formation under standard conditions of cyclohexane is actually really difficult to work out experimentally. So what do? Well, we need to find another route, like we did before, or something in common that we can use to get two routes out of. And what I'm going to do is I'm going to say, right, okay, well, what do we know about carbon and hydrogen? Well, we know that both of them burn. And we know that cyclohexane can burn as well. So, in that case, carbon burns to make carbon dioxide, and cyclohexane burns, and that also makes carbon dioxide. Hydrogen burns to make water. Don't forget the state symbols, Mr. Mitchell. And seriously, don't forget the state symbols. And if we balance this out, then we find that actually if we burn it in excess oxygen, we will end up with 6 carbon dioxide molecules for our 6 carbons, and we'll end up with 6 molecules of water for our hydrogen. We'll also end up with the same if we burnt our 1 molecule of cyclohexane. We'd end up with 6 CO2 and 6 H2O. Now it's worth mentioning here that there would be oxygen involved, obviously, and I could put oxygen on this side of the equation here to show oxygen plus that going to here, and I could put, but I'd also need the same amount of oxygen here. So because they cancel out of the one I'm interested in, I'm not going to include it in my example. I'm going to assume that the oxygen here and here are the same, which it in theory should be. Now those of you who are more eagle-eyed than others will have noticed that actually what we're doing here is if we're taking these in standard states and standard conditions, then what we've actually got here is we've got the standard enthalpy change of combustion of cyclohexane, and over here we've got the standard enthalpy change of combustion of carbon and the standard enthalpy change of combustion of hydrogen. It's basically what we're doing. We're burning all 3 of these. It's a bit more complicated because, of course, if we were to look at the standard enthalpy change of combustion of hydrogen, that would be for 1 mole of hydrogen. So when we look at this one, we've actually got to multiply that number by 6. And when we look at this one, we've got 6 moles of carbon. So the data for the enthalpy change of combustion of carbon is for 1 mole. So we've got to multiply that by 6 as well. Here, this is 1 mole, and therefore this data doesn't need to be changed. Now you'll find in any good data book or in any good exam paper a table which looks a little bit like this. And this will have a substance and it'll have some thermodynamic data, and we can plug those numbers in to our equation. So for example, here I've written it in blue. We have 6 minus 394s, because that's what it said in the table, and we have 6 286s, because that's what it said in the table, and over here, this just in the table, we have 1 of what it says on the table, so we've got minus 3656.8. So now we've got some numbers there, and of course because I've got these 2 that I've multiplied by 6, really I should put those as the solution to that. So I've multiplied them by 6, I have that number and that number. Now adding those 2 negative numbers together will give me this number here. So all I've done there is I've plugged in the numbers and ended up with a value here for this enthalpy change and a value here for this enthalpy change. Now this is where it gets a bit complicated. So we are not going from here to here because this arrow is actually going this way. What we're saying is that this route here from here to here is the same as this route here from here to here. So, when we come to write our equation, our delta FH under standard conditions will be added to, because that's this way round, minus 3656.8, and I'm going to call that the red root, and that will equal what I'm going to call the purple root. They go to the same place, they must be equal. So what I'm going to do to make this easier on myself is, as I'm doing a question on this, or if I'm trying to calculate this, I'm going to put my negative numbers in brackets like this, and you see I've left the plus sign where it is. I haven't tried to do anything fancy with cancelling that out. Now if you're confident that you can do that, then do it, but I find it just gets confusing if you try to simplify things too soon. Now we can start to rearrange it, because if we want to know that, we need to take this, and that will equal this minus this negative number. So delta FH under standard conditions should equal minus 4080, which was the term I had there before, minus 3656.8, which is the term I had before. Again, I haven't simplified anything out yet. Now, if I type this into my calculator exactly as this, using the brackets, I will get the right answer out. So that leaves us with minus 423.2 kilojoules per mole.